The Einstein-de-Haas experiment is a famous experiment in physics. It proved that magnetism is caused by the spinning of electrons. This experiment was first done in 1915 by Albert Einstein and Wander Johannes de Haas. In the original experiment, a metal cylinder was hung from a thin wire. This cylinder was surrounded by a coil of wire. When an electric current was passed through the coil, it created a magnetic field. This magnetic field caused the electrons in the metal cylinder to align their spins. The aligned spins, in turn, caused the cylinder to rotate slightly. This rotation proved that the spinning electrons were responsible for the cylinder's magnetism. The Einstein-de-Haas experiment can be modified using a special material called a ferrite core. A ferrite core is a ceramic material that is very good at conducting magnetic fields. In this modified setup, the ferrite core is placed inside the coil of wire. When microwave power is applied to the coil, it creates a rapidly changing magnetic field. This changing field interacts with the electrons in the ferrite core, causing them to align their spin. The interaction between the microwave power and the ferrite core leads to a phenomenon called ferromagnetic resonance. At this resonance, the ferrite core starts behaving in a very unusual way. It develops something called negative permeability. Permeability is a measure of how easily a material can be magnetized. Normally, materials have positive permeability, meaning they become magnetized in the same direction as an applied magnetic field. However, at resonance, the ferrite core exhibits negative permeability. This means it becomes magnetized in the opposite direction to the applied field. This negative permeability has a very interesting effect. It causes the magnetic field inside the ferrite core to become zero, even though there is an external magnetic field. This is similar to what happens in superconductors, materials that expel magnetic fields from their interior, a phenomenon known as the Meissner Effect. The microwave power excitation of the ferrite core does not just cause the electrons to align, it also causes them to jiggle and vibrate rapidly. This rapid movement creates tiny whirlpools of magnetic energy within the ferrite core called flux vortices. These flux vortices behave like tiny magnets with only one pole, called magnetic monopoles. Magnetic monopoles are hypothetical particles that have never been observed directly, but their existence is predicted by some theories of physics. These magnetic monopoles, created within the ferrite core due to the unique conditions of the experiment, are believed to possess very high energy levels. Some scientists believe that these high energy levels could be the key to achieving room temperature superconductivity. The cylindrical shape of the ferrite core is important because it helps to confine these flux vortices and enhance their stability. This, in turn, could lead to more stable and controllable magnetic monopoles and potentially pave the way for room temperature superconductivity. If achieved, room temperature superconductivity would revolutionize many fields, from energy transmission to transportation.